the kinetic molecular theory. We want to discuss the meaning of temperature. When we talk about temperature, the Kelvin temperature is an index of the random motion of particles in a gas. So the higher the temperature, the higher the average kinetic energy of the particles, and the greater their motion. So here's an equation that enables us to relate the average kinetic energy of particles in a gas sample. And that's 3/2 RT, where R is going to equal 8.31 joules per mole Kelvin. So we have two problems here. Calculate the average kinetic energy of nitrogen gas in a sample at 273 Kelvin and 546 Kelvin. Now the fact that it's nitrogen gas has nothing to do with the particular problem. So for our first temperature, kinetic energy average will equal 3/2 8.31 joules per mole Kelvin times 273 Kelvin. And our temperature has to be in Kelvin so that our Kelvin values cancel out. And we'll be given 3,403 joules per mole as our average kinetic energy of those gas particles. Now for our second temperature, kinetic energy average equals 3/2 8.31 joules per mole Kelvin times 546 Kelvin. And when we plug that in, we get 6,806 joules per mole. So when we look at this, as the temperature goes up, the average kinetic energy of particles increases. Next, we want to deal with the root mean square velocity. And this is the square root of the average of the squares of the individual velocities of gas particles. So URMS is our root mean square velocity, and that equals the square root of 3RT over M, where M equals the molar mass of the gas. The R value that we're going to use again is 8.31 joules per mole. And when you think about that, you want to find a velocity, and there's no unit in that unit that deals with velocity. But joules actually equals kilogram meter squared per second squared, which eventually will give us meters per second when we're done with our problem, and that gives us the velocity. So here's our question. Calculate the root mean square velocity for the atoms in a gas of helium at 25 degrees Celsius. Now, we look up helium on the periodic table, and it tells us its molar mass is 4.00 grams per mole. Now, when we plug all this into the equation, we're going to have an issue, because our R value is in kilograms and our molar mass is in grams. So we're going to convert our grams per mole to kilograms per mole. So we're going to get 0.00400 kilograms per mole, and then our units will eventually cancel out. So our root mean square velocity will be the square root of 3 times 8.31 kilogram meters squared per second squared mole Kelvin. And we'll multiply that by our temperature, which has to be in Kelvin so it cancels out. So 298 Kelvin. And we'll divide that by 0.00400 kilograms per mole. Now, when we look at this problem, because we did our conversion, our kilograms will cancel out, our moles will cancel out, our Kelvin will cancel out, and we're going to be left with meters squared per second squared, and when we take the square root of that, that'll give us meters per second, which are our units for velocity. So our root mean square velocity for these particles is 1,363 meters per second. The kinetic molecular theory. When we've been dealing with our ideal gas law problem so far, we have made an assumption about the gases we were dealing with. We assumed that the gas particles were in fact ideal gases. But when we look at gases, no gas is truly ideal. Many gases come close to ideal behavior under certain conditions. So what we want to do is we want to talk about defining what an ideal gas is, comparing it to real gases, and making some correction factors between the two. So the first part of our kinetic molecular theory, which discusses what an ideal gas is that the particles in a gas are so small compared to the distance between them in the volume of the container that the volume of the individual particles can be assumed to be zero. Our second statement about the kinetic molecular theory deals with the interaction between particles. It says that the particles are in constant motion. The collisions of the particles with the walls of the container are the cause of the pressure exerted by the gas. In other words, the particles don't exert any pressure on each other. Our third statement is that the particles are assumed to exert no forces on each other. They don't have an attractive force or a repulsive force between them. And our fourth is that the average kinetic energy of a collection of gas particles is assumed to be directly proportional to their Kelvin temperature. Now, real gases do have a volume. So saying that that volume is so small that it's negligible really isn't true. And ideal gases do approach ideal behavior. Ideal gas law works best when we're at low pressures and high temperatures. Why? All right, well, let's look at a couple of factors. Two things happen when gases are packed closely together. Okay, first, the volume of the gas molecules becomes more significant. The less space there is between them, the more significant the volume of the actual particles becomes. And two, if the gas particles are closer together, they're going to have a greater attraction towards each other and stick together. So, van der Waals developed an equation to take the ideal gas law and apply it to real gases. He made what are called correction factors for the difference between an ideal gas and a real gas. Now, you're never going to be asked to actually calculate using this equation, but we want to talk about the different variables. So the first thing we should notice is that we've got PV equals nRT. There's our ideal gas law equation. But there are two things about gases that make them not ideal. So we're going to have a correction factor here for pressure and a correction factor here for volume. Our first correction factor accounts for the fact that there are interactions between the particles. And the correction factor will help to make the pressure higher. In other words, particles don't just exert a pressure on the container, but they also exert a pressure on each other. And adding those two values together would give us a more ideal value for pressure. Our second correction factor deals with the fact that particles do take up space in the container. So we're going to subtract the volume of the molecules from the individual container, and that will give us a better reading of the volume of the ideal gas. So, why high temperatures and low pressures? High temperatures means the particles have higher kinetic energies. If they have higher kinetic energies, they're going to be moving around more. And if they're moving around more, there's going to be less time for them to interact. Low pressures means that the particles are going to be spread out more. The particle size is going to be less significant than it would be if they were closer together. So here's a question. All right, equal molar quantities of two gases, oxygen and water vapor, are confined in a closed vessel at a constant temperature. Which gas, if any, has the greater partial pressure? All right, so let's look at this. We've got P, oops, forgot to turn the pen on. We've got PV equals nRT. We know that equal molar, so this is constant, R is always constant. It says a constant temperature, and they're in the same container. That means that both gases are exerting the same pressure. Which gas, if any, has the greater density? All right, so when we think about the density, we've got our molar mass equals dRT over P. So molar mass and density are directly related when temperature and pressure are held constant. So the one with the higher molar mass is the one that's going to have the higher density, so oxygen gas has a higher density. Which gas, if any, has the greater concentration? Well, concentration is in terms of moles per liter. It says equal molar, and it says they're in the same container. So their concentrations are the same. Five says, which gas, if any, will show the greater deviation from ideal behavior? When we look at water molecules, because they're polar molecules, they're going to tend to be attracted to each other. Oxygen molecules are nonpolar. They're not going to have much of an attraction for each other. So since we've got an attraction between the water molecules, there's going to be a greater interaction between them, so they're going to deviate the most from ideal behavior. And our last problem says, which gas, if any, has the greater average molecular speed? Okay, well, the greatest average molecular speed, again, if we look at that equation, our molecular speed is going to be indirectly related to its mass. The heavier it is, the slower it moves. The lighter it is, the faster it moves. So since water vapor has a lower molar mass, it's going to have a higher average molecular speed.